All right, let's get right into it. We're all getting used to AI that can write amazing text or generate mind-blowing images. But what happens when you smash those two worlds together? When an AI has both eyes and a voice, how do we really know if it understands what it's seeing?
I mean, that sounds like a question straight out of a sci-fi movie, right? But it's not science fiction anymore. The most advanced AI models today are literally being built to perceive the world in a way that's kind of like how we do it by combining different senses. But here's the kicker. Just seeing something isn't the same as understanding it. And that's where the real challenge kicks in. So this whole challenge is pushing us into a brand new era, the era of multimodal AI. And let me tell you, it's a massive jump from the text-only chatbots we've all been playing with. So what exactly is a multimodal large language model, or MLLM? Well, researchers have this awesome way of thinking about it. Picture a powerful language brain, like the GPT models we're all familiar with. Now, connect that brain to sensory organs. These are things like vision encoders that let it see, or audio encoders that let it hear. And what you get is an AI that's way more than just a text bot. Think about it. It could look at a meme you send it and actually get the joke. Or you could show it a super complicated financial chart and it could just tell you what's going on. It's all about connecting what it sees with language so it can reason about the world more like we do. Okay, so how in the world do you actually build one of these things? It's a really cool process of plugging all these different parts together and then teaching them to speak the same language. On a basic level, it's pretty brilliant. First, you've got this thing called a vision encoder. Think of it as the AI's eye. It looks at an image and kind of chops it up into digital pieces. But, and this is a big but, the LLM brain doesn't speak image. It only speaks text. So you need a translator, right? That's where this critical piece called a projector comes in. It takes all that visual info and turns it into a language the LLM can actually process. Now, getting this whole system to work is like sending it to school. It's a 3-step journey. Step 1, alignment pre-training. This is kindergarten, basically. The AI learns to connect a picture of a cat with the word cat. Simple stuff. Then step 2 is instruction tuning. Now it's learning to follow directions, like tell me if the cat in the picture looks happy or sad. And finally, the last step is all about aligning it with what we humans actually want. You've probably heard of this. It's called RLHF, or Reinforcement Learning from Human Feedback. It's basically giving the AI a gold star when it gives a good, helpful, safe answer. So we've built it. This super powerful brain with eyes and ears. It seems to work, but here's the million-dollar question. Does it really? And proving that, well, that's one of the single biggest headaches for AI researchers right now. And just look at the scale of this problem. This is not like giving the AI a simple multiple choice test. No way. Testing an MLM is like putting it through the Olympics, a PhD defense, and a medical board exam all at once. It's a huge, huge undertaking. So what kind of stuff are they even testing for? It's so much more than just what is this a picture of? It's things like, can it tell the difference between a cat on the table and a cat under the table? Does it have basic common sense? Does it just make things up, hallucinate stuff that isn't even there? What about bias, safety? Can it tell if someone is waving goodbye or hailing a cab? Each one of these things, every single one, needs its own special test. All of this complexity brings us to the absolute core of the problem. It's a fundamental paradox that researchers have a name for, the evaluation trilemma. I want you to picture an impossible triangle. On each corner, there's something you desperately want for a good AI test. The problem? You can't have all three at the same time. It's just not possible. Okay, so here's how the trade-off works. First, you want wide coverage, right? You want to test everything. But testing everything is super expensive and takes forever. So that clashes with goal number 2, low cost. And here's the real kicker. The simplest way to keep costs low is to just use data that's already out there. But if you do that, you run smack into the third goal, zero contamination. You have to be sure the AI hasn't already seen the test answers in its training data. So you get to pick 2. Wide coverage and low cost, you risk contamination. Wide coverage and zero contamination, it's going to cost a fortune. You see the problem. You just can't get all 3. Let's dig into that last one, contamination, because it's a really wild problem. Seriously, how do you give a test to a student who might have already memorized the entire answer key? And one of the key papers on this topic says it perfectly. Data contamination can totally skew the scores. It makes the AI look smart when really it might just be spitting back something it saw during training. And get this isn't just a what-if scenario. Researchers have literally gone digging and found images from the tests, the exact same images, inside the model's training data. It's exactly like finding the final exam with all the answers printed in the back of your textbook. The AI isn't thinking, it's just remembering. So, okay, why does any of this matter? Who cares about test scores? Well, because this isn't about getting an A on a report card. This is about whether we can build AI that we can actually truly trust when it counts. Let me give you a really concrete example. There's this brand new, super careful test for spatial reasoning. Understanding if something is to the left or to the right or behind something else. Super basic stuff for us. The best, most advanced MLLM scored 48.14%, less than a coin flip. It was basically just guessing.
And humans? How did we do on that exact same test? 98.4%. That is a massive difference. It just shows you how huge the gap is between what we think these AIs can do and what they can actually do. For things that are completely fundamental to us, they've still got a long, long way to go.
And that right there is the whole point. Building these really hard, really clean tests isn't just some boring academic thing. It is absolutely essential if we want to build AI that's actually reliable, AI we can trust with the important stuff, like analyzing medical scans or driving a car. So it all comes down to this one final question. As these AIs get more and more woven into the fabric of our lives, we have to ask ourselves, if we can't test them perfectly, and if they can essentially cheat on those tests, then how can we ever truly trust them?